Assalamu alaikum. In this video, I'll explain the solution of the translated questions. First question, given an event restoring numeric values, design an algorithm to efficiently return the sum of all values within the given range L to R. Okay, an AVL tree is self-balancing binary search tree. To find the sum of all values between L to R, we use the BST property. Now, what is BST property? BST property is that each node value is greater than the left child value and less than the right child value. So, how the algorithm can approach: if node value is less than L, then search for right subtree, and if node value is greater than R, then search for left subtree, and if it is in the range of L to R, then add the node value, explore both sides. And we also store the subtree sum for each node to reduce the repeated computations. And this approach also skips the unnecessary branches and keeps the process efficient. Now the follow-up question: how would it approach scale if each tree update must propagate features for downstream ML models? If we consider each node represents feature, then updating one node automatically updates the downstream model inputs. If each node propagate the ML features, then maintain aggregate features per node. If any node changes, then we must just update the feature related to that node or related to root to that node or any branch to related that feature, and it will propagate automatically for the downstream ML models. Now the second question, suppose you must store and retrieve large model weight files distributed across a database. Explain how a B-tree supports fast search and insert operations at scale. A B-tree is a multi-level balance structure used in database. Here each node stores such a multiple sorted keys and pointers to child nodes or data blocks. Now how it supports fast search. Fast search, as we know that each node contains sorted keys, so we can also apply binary light search. It also follows the BST properties, like the node in the right part also contain the keys that are greater than the parent node keys, and the left child also contain the keys that are less than the parent keys. So we can also search like that. If the value is greater than the parent node, then we just go for the right subtree. If it is less than the left subtree, so it can also reduce the search space like n by 2. And for first insertion, as that each node contains the sorted keys, that means we can must insert the values like that, and it can be sorted in the last line. That splits the full nodes to stay balanced. It's ideal for large databases, indexing, and model storage. Follow-up: how does this apply to feature vector lookups in recommender system? So what is feature vector? Feature vectors are that vectors can be row or column vectors of features. So recommender system that can recommend us something. So if we consider about the e-commerce system where users can buy things or also search for things, it can recommend the products based on the past experience of user. If user buy some things or search some things in past, then it can also recommend something future on those searches or buying things. So we can use like two types of B-tree. For one is user and one is for products. So a B-tree which can also store the key values for the users and also the user feature vectors, and also other B-tree also stores the keys of the products or ID and also for the feature vector. Now we also check for each product to the user and which feature vector is nearest to the user feature vector lookups. Then which one is give better, then we can choose that product and recommend the system. Like here B-tree enables the quick retrieval and update at massive scale. So we can apply this to feature vector lookups in recommender system. Now the third one, outline an algorithm for finding a minimum spanning tree in a distributed system. In a distributed system, we know each node knows its neighbors and each weights. We can use the Gallagher-Hamlet-Speed algorithm for distributed MST. Now, how can the algorithm can be approached? That each node starts as a separate fragment. That means each node considered as a fragment to itself. Then find the minimum outgoing edge from that fragment and merge the fragments using the smallest connecting edge. That means we find the minimum edge and then merge them together and repeat it until one MST spans to all nodes. That means until we can form the fragments which contains all the nodes and no cycle formed. The follow-up: in what real-world scenario you would use the MST? It's like if sensor network feature selection, where we can consider each node is a sensor, and as MST give the unique graph, so we can use this, that MSTs are used for sensor network feature selection connected to correlator sensor with minimal redundancy and also reduce the cost. And it also perfect for network optimization. Now the last one, for a tree or graph based feature index in a memory constrained environment, compare the slab allocation or garbage collection on memory management strategies. Tree or graph based feature indexes even need efficient memory management. So slab allocation like is that pre-locate fixed size memory blocks or slabs, extremely fast and predictable location, but great for real-time low latency system. And garbage collection automatically reclaims unused memory and is dynamic. Simplify the management, introduce unpredictable pauses. So if we comparison, that slab allocation is good for if we want to predictable latency or like high performance, and garbage collection is that it is easier, but if there is a garbage collection pause, then it can be causes for high latency. Then follow up, which open option better supports predictable latency for online serving in email. If we want to want that system support the predictable latency, then we must use the slab allocation, that as we have fixed size memory, then it can be easily predictable the latency or late for the response in online serving. And is also guarantee the stable performance as there is no type of pause. So that's all for now. Thank you.